Hello, and welcome. It's good that you're here, wherever you are right now. Perhaps you've had a long day, or perhaps you're simply looking for a quiet place to rest your mind. Either way, you've arrived at the right moment. There's no need to do anything but listen, or let the words wash over you like a gentle tide. You can close your eyes if you wish. You can let your breathing slow. You can simply be here, in this calm space, while we explore something beautiful together. Tonight, we're going to talk about magnetic fields in nature. I know that might sound technical at first, but I promise you, there's nothing to worry about. We're not here to memorize formulas or struggle with complexity. We're here to discover something quietly extraordinary, something that surrounds you right now, even as you rest. Magnetic fields are invisible, yes, but they are also ancient, gentle, and everywhere. They hum through the earth beneath you. They guide birds across continents. They shimmer in the sky as curtains of light. And tonight, we'll wander through these wonders together, slowly, with no rush at all. If you enjoy this kind of journey, you're welcome to follow along for more. But there's no pressure. You can simply stay here, in this moment, and let the facts arrive like soft waves. Let's begin. Magnetic fields are, at their most basic, invisible lines of force. You cannot see them with your eyes, cannot touch them with your hands, yet they shape the world in profound ways. Imagine a field of influence stretching out from a magnet, curving gently through space, connecting one pole to another. These lines have no weight, no color, no sound. They are silent architects, organizing iron filings into elegant patterns, guiding compass needles toward north, holding the very atmosphere of our planet in place. And the most comforting thing about them is this: they have always been there, long before humans, long before language, quietly doing their work. The Earth itself is a giant magnet. Deep below your feet, thousands of miles down, the planet's core churns with molten iron and nickel. This liquid metal moves in vast, slow currents, driven by the heat of the Earth's interior. As this metal flows, it generates electric currents, and those currents, in turn, create a magnetic field. This process is called the geodynamo, and it has been running for billions of years. It requires no fuel, no maintenance, no intervention. It simply is. And because of it, the Earth is wrapped in a magnetic cocoon, a protective shield that extends far out into space. This magnetic field is not perfectly symmetrical. If you could see it, it would look a bit like the field around a bar magnet, with lines arcing from the south magnetic pole to the north. But the Earth is not a simple bar magnet. It wobbles. It shifts. The magnetic poles drift slowly over time, wandering across the surface of the planet. Right now, the North Magnetic Pole is moving through the Canadian Arctic, heading towards Siberia at a pace of about 30 miles per year. This is not something to fear. It's simply the Earth breathing, adjusting, continuing its ancient rhythms. The strength of the Earth's magnetic field is gentle. If you were to measure it, you'd find it's only about half a Gauss at the surface, roughly 100 times weaker than a refrigerator magnet. And yet, this faint field is enough. It's enough to turn a compass needle. It's enough to shield us from the solar wind. It's enough to make life on Earth possible. There's something deeply reassuring about that, isn't there? That such a quiet force can do so much. Birds can sense this magnetic field. Migratory species like robins, geese, and swallows travel thousands of miles each year, crossing continents and oceans, and many of them navigate using the Earth's magnetism. Scientists believe that some birds have tiny crystals of magnetite in their beaks or brains, crystals that act like biological compasses. Others may have special proteins in their eyes, proteins that change chemically in the presence of a magnetic field, allowing the bird to literally see the field as patterns of light or shadow. Imagine that. A robin looking at the sky and seeing not just blue, but also the invisible lines of the Earth's embrace, guiding it home. Sea turtles, too, are magnetic travelers. Loggerhead turtles hatch on beaches in Florida, scramble into the ocean, and then disappear into the vastness of the Atlantic. For years, they drift with the currents, circling the entire ocean in a great loop. And when they are ready to return, they navigate back to the very same beaches where they were born. How? They remember the magnetic signature of their birthplace. Different parts of the ocean have slightly different magnetic intensities and angles, and the turtles can sense these differences. They carry a map inside them, written in magnetism, and it never fades. Salmon do something similar. After years at sea, they return to the exact river, even the exact stream where they were born. They use smell, yes, but they also use the Earth's magnetic field to find their way back to the coast. It's as if the world is covered in invisible signposts, and these animals can read them effortlessly. There's no stress in this, no confusion, just a quiet knowing, an ancient conversation between creature and planet. Even bacteria respond to magnetism. There are tiny organisms called magnetotactic bacteria that live in ponds, lakes, and oceans. Inside their bodies, they grow chains of magnetic crystals, little magnets arranged in a row. These crystals align with the Earth's magnetic field, and they pull the bacteria downward, toward the sediment at the bottom of the water, where oxygen is scarce and conditions are just right for them. These bacteria are so small you'd need a microscope to see them, yet they are tuned to the planet's magnetism with perfect precision. They've been doing this for billions of years, long before any bird took flight or any turtle swam. The sun has a magnetic field too, and it is far more powerful than Earth's. The sun is a boiling sphere of plasma, a state of matter so hot that electrons are stripped from atoms, leaving charged particles swirling in vast currents. These currents generate magnetic fields that twist and loop through the sun's atmosphere. Sometimes these loops break and reconnect, releasing enormous bursts of energy called solar flares. Other times, they erupt outward, hurling billions of tons of charged particles into space. These eruptions are called coronal mass ejections, and when they reach Earth, they interact with our magnetic field in beautiful ways. When particles from the sun collide with Earth's magnetic field, they are funneled toward the poles. There, they spiral down along the magnetic field lines and collide with molecules in the upper atmosphere. These collisions release energy in the form of light, and that light is what we call the aurora. In the north, it's the aurora borealis. In the south, the aurora australis. The colors depend on which molecules are struck. Oxygen gives off green and red light. Nitrogen glows blue and purple. The result is a shimmering curtain of color draped across the night sky, a visible manifestation of invisible forces. And it's all perfectly safe. The magnetic field absorbs the energy, protects us, and turns it into art. The aurora has been witnessed for thousands of years. Ancient peoples saw it and created myths to explain it. Some thought it was the spirits of the dead dancing in the sky. Others believed it was a bridge to the heavens. The Inuit told stories of the lights as ancestors playing a game with a walrus skull. The Norse imagined the Valkyries riding across the sky. All of these stories share a sense of wonder, a recognition that something sacred was happening. And in a way, they were right. The aurora is a meeting place between Earth and Sun, a conversation written in light. You don't have to travel to the Arctic to experience the effects of magnetic fields. Right now, as you rest, the Earth's field is passing through you. It's incredibly weak at the scale of your body, far too weak to feel, but it's there. Some scientists have wondered whether humans might have a latent magnetic sense, hidden somewhere in our biology. Studies have shown that certain human cells contain magnetite crystals, just like those in birds. Could we, at some deep, forgotten level, sense the Earth's magnetism? It's a beautiful question, one without a final answer yet. But even if we can't sense it consciously, It's comforting to know we're held in that field, always. Magnetic fields also exist in rocks. When lava erupts from a volcano and cools, the iron-rich minerals inside it align with the Earth's magnetic field at that moment, like tiny compass needles freezing in place. Once the rock solidifies, that alignment is locked in. This means that rocks carry a memory of the Earth's magnetic field from the time they formed. Geologists can study these rocks and reconstruct the history of the planet's magnetism, going back millions of years. They've discovered that the Earth's magnetic field has flipped many times, with north and south switching places. These reversals happen slowly, over thousands of years, and they leave a record in the stone. The ocean floor is covered in stripes. As new crust forms at mid-ocean ridges, it records the current direction of the magnetic field. When the field flips, the new crust records the reverse direction. Over time, this creates a pattern of alternating magnetic stripes, spreading out symmetrically from the ridge. It was the discovery of these stripes in the 1960s that helped confirm the theory of plate tectonics. The Earth's surface is not static. It moves, shifts, renews itself, and the magnetic field has been quietly recording that movement all along. Some animals use magnetic fields to find food. Sharks and rays have special organs called ampullae of Lorenzini, tiny jelly-filled pores around their heads that can detect electric and magnetic fields. When a fish moves through the water, it generates a faint electric field. The shark senses this and knows exactly where the fish is, even if it's buried in the sand. The Earth's magnetic field also helps them navigate across vast stretches of ocean. They are tuned to the planet in ways we're only beginning to understand, moving through the water with a calm, ancient confidence. Lobsters and spiny lobsters migrate along the ocean floor, sometimes traveling in long, single-file lines. They use the Earth's magnetic field to stay on course. Even in the dark, even in murky water, they know which way to go. There's no panic, no second-guessing, just a steady march, guided by invisible lines of force. It's a reminder that the world is full of guidance, even when we can't see it. Bats, too, may use magnetism. Studies suggest that some bat species can sense the Earth's magnetic field and use it to orient themselves when they leave their roosts at dusk. They fly out into the night, navigating by echolocation, yes, but also by a deeper sense of direction, a sense rooted in the planet itself. It's as if the Earth is always whispering to them, "This way. You're safe. Keep going." Magnetic fields can even affect the growth of plants. Some studies have shown that seeds exposed to magnetic fields germinate faster or grow more vigorously. The mechanisms aren't fully understood, but it seems that magnetism can influence the movement of ions and molecules within plant cells, subtly altering their biology. This doesn't mean you should put magnets in your garden, but it does suggest that life is sensitive to these invisible forces in ways we're still discovering. The world is more connected than it appears. Honeybees are also thought to sense magnetic fields. They use the sun and polarized light to navigate, but magnetism may play a role too, especially on cloudy days when the sun is hidden. Inside the hive, bees perform their famous waggle dance to tell other bees where to find flowers. The precision of this dance suggests a deep spatial awareness, an understanding of direction and distance. Magnetism might be part of that awareness, another layer in the bee's rich sensory world. Even humans have built tools to interact with magnetic fields. The compass, one of the oldest navigational instruments, is simply a magnetized needle free to rotate. It aligns with the Earth's field, pointing toward magnetic north. For centuries, sailors used compasses to cross oceans. Explorers used them to map continents, and travelers used them to find their way home. The compass is a bridge between the invisible and the visible, a way of seeing what cannot be seen. And it asks nothing of us but trust. Magnetic resonance imaging, or MRI, uses powerful magnetic fields to see inside the human body. The machine generates a field tens of thousands of times stronger than Earth's, and it causes hydrogen atoms in your body to align. Then, pulses of radio waves nudge those atoms, and as they relax back into place, they emit signals. Those signals are translated into images, revealing soft tissues, organs, the brain. It's a way of looking inside without cutting, without harm. The magnetic field, so gentle in nature, becomes a tool of healing in our hands. The planets in our solar system have magnetic fields of varying strengths. Jupiter's field is the strongest, about 20,000 times more powerful than Earth's. It's generated by currents in a vast ocean of liquid metallic hydrogen deep inside the planet. This field traps charged particles in enormous radiation belts, far more intense than Earth's Van Allen belts. Jupiter's magnetosphere is so large that if you could see it from Earth, it would appear bigger than the full moon. It's a giant, invisible fortress surrounding the planet and its many moons. Saturn has a magnetic field too, though weaker than Jupiter's. What makes Saturn's field unusual is how perfectly aligned it is with the planet's rotation axis. Most planets, including Earth, have a tilt between the magnetic and rotational axes. But Saturn's field is almost perfectly symmetrical, a mystery that scientists are still trying to understand. It's as if Saturn is holding itself in perfect balance, a quiet giant spinning in the dark. Mars once had a strong magnetic field, but it faded billions of years ago. Without it, the solar wind gradually stripped away much of the Martian atmosphere, leaving the planet cold and dry. The loss of the magnetic field was a slow catastrophe, unfolding over millions of years. But even now, there are patches of magnetism in the Martian crust, remnants of the ancient field, frozen in stone. They're like ghosts, echoes of a time when Mars might have been more like Earth. Venus has almost no magnetic field at all. It rotates so slowly, once every 243 Earth days, that it can't generate a dynamo in its core. Without a magnetic field, the solar wind interacts directly with Venus's thick atmosphere, stripping away particles and shaping a long magnetic tail that stretches out behind the planet. Venus is unprotected, exposed, yet endures. Its atmosphere is so dense that it shields the surface in other ways. Life finds a way, or at least, worlds find a way to persist. Mercury, despite being small, has a magnetic field. It's weak, only about 1% the strength of Earth's, but it's there. Scientists think it's generated by a partially liquid core, still churning after billions of years. Mercury is a tiny world, baked by the sun, yet holds onto this faint magnetic shield. It's a reminder that even the smallest places can have hidden depths. The gas giants, Uranus and Neptune, have strange, tilted magnetic fields. Unlike Earth's relatively orderly field, theirs are offset from the center of the planet and tilted at sharp angles to their rotation axis. This creates chaotic, tangled magnetospheres, unlike anything else in the solar system. Scientists think these fields are generated not in the core, but in layers of slushy, electrically conductive ices deep inside the planets. It's a different kind of dynamo, a different kind of magnetism. The universe is full of variations, each one a new way of being. Magnetic fields exist beyond our solar system too. Neutron stars, the collapsed cores of massive stars, have the strongest magnetic fields known in the universe. Some neutron stars, called magnetars, have fields a trillion times stronger than Earth's. If a magnetar were located halfway to the moon, it could erase the data on every credit card on Earth. These fields are so intense that they warp the very fabric of space around them. And yet, even these extreme fields follow the same basic principles as the gentle field that surrounds you now. Magnetism scales, from the smallest bacteria to the most violent stars, and it remains, at its heart, a quiet force of alignment and connection. Our Milky Way galaxy has a magnetic field too. It's incredibly weak, millions of times fainter than Earth's, but it stretches across thousands of light years. This galactic field is generated by the motion of charged particles in the interstellar medium, the thin gas and dust between the stars. It shapes the way cosmic rays travel, influences the formation of new stars, and threads through the spiral arms of the galaxy like invisible stitching. When you look up at the night sky, you're looking through this field. It's holding the galaxy together, in a sense, not through gravity alone, but through this ancient, pervasive magnetism. Cosmic rays, high-energy particles from distant supernovae and other violent events, travel through space at nearly the speed of light. They spiral along magnetic field lines, guided by the fields of stars, galaxies, and the interstellar medium. Without these fields, cosmic rays would travel in straight lines, and the universe would be a very different place. But the fields bend their paths, scatter them, diffuse them. This means that when a cosmic ray finally reaches Earth, it has been on a long, winding journey, shaped by magnetism every step of the way. Even the most energetic particles in the universe are subject to this gentle guidance. The sun's magnetic field reverses every 11 years, during the peak of the solar cycle. Sunspots, dark patches on the sun's surface, are regions of intense magnetic activity. They appear in pairs, with opposite magnetic polarities. As the cycle progresses, the number of sunspots rises and falls, and the sun's overall field weakens, collapses, and then rebuilds with the poles flipped. This cycle has been observed for centuries, and it's as regular as a heartbeat. The sun breathes in magnetism, and we feel the effects here on Earth in the form of auroras, geomagnetic storms, and subtle changes in our own magnetic field. Geomagnetic storms sound dramatic, but most of them are harmless. When a strong burst of solar wind reaches Earth, it compresses our magnetic field and sends ripples through it. These ripples can induce electric currents in power grids, sometimes causing blackouts, but usually everything adjusts and continues. Satellites in orbit are more vulnerable, as they sit outside the thickest part of the atmosphere and are exposed to higher levels of radiation during storms. But even then, engineers design satellites with shielding and backup systems. The storms come and go, and life continues. The Earth's magnetic field absorbs the impact, flexes, and holds. The northern and southern lights are not just beautiful. They also produce sound, though it's rare and faint. Some people in the far north have reported hearing crackling or whooshing noises during intense auroras. Scientists think these sounds might be caused by changes in the electric field near the ground, which could create small sparks or discharges in the air or on surfaces. The sounds are elusive, hard to record, but those who have heard them describe a sense of presence, as if the sky itself were alive. It's a reminder that the aurora is not just light, but energy, movement, a dynamic interaction between worlds. Magnetic fields can also trap particles for a long time. Earth's Van Allen radiation belts are regions of space where charged particles from the solar wind are captured by the magnetic field and held in place, spiraling back and forth along field lines. These belts were discovered in 1958 during the early days of space exploration, and they were a surprise. They're shaped like two donuts, one inside the other, encircling the Earth. Astronauts traveling to the moon had to pass through them quickly to avoid excessive radiation exposure. But the belts also protect us, trapping particles that might otherwise reach the surface. They're a natural shield, constantly at work. The Earth's magnetic field has weakened by about 10% over the past 2 centuries. Some people worry this means a reversal is coming soon, but soon, in geological terms, could mean thousands of years. Reversals themselves are not catastrophic. They happen gradually, and life has survived many of them. During a reversal, the field doesn't disappear. It just becomes more complicated, with multiple poles appearing and shifting. Compasses will be less reliable, and we'd see more auroras at lower latitudes. But the atmosphere would still protect us from radiation, and the field would eventually settle into a new configuration. The Earth has done this before, many times, and it will do it again. It's part of the planet's natural rhythm, nothing to fear. Magnetic fields can be found in the smallest scales too. Atoms themselves have tiny magnetic fields generated by the motion of electrons around the nucleus. In most materials, these atomic magnets point in random directions, canceling each other out. But in certain materials, like iron, cobalt, and nickel, the atomic magnets can align, all pointing the same way. When this happens, the material becomes magnetic. This alignment can be triggered by an external magnetic field, or it can occur naturally as the material cools. Once aligned, the atomic magnets reinforce each other, creating a field that extends beyond the material itself. This is how permanent magnets are born, from the quiet cooperation of countless tiny magnets, each one contributing to the whole. Lodestone is a naturally magnetic rock, a form of magnetite that has been magnetized by lightning strikes or the Earth's field. Ancient peoples discovered lodestone thousands of years ago and were amazed by its properties. It could attract iron, and if suspended or floated, it would align with the Earth's field. This was humanity's first encounter with magnetism, a mystery that seemed almost magical. Lodestone was used in early compasses, and it sparked centuries of inquiry into the nature of magnetism. It's a humble rock, dark and unassuming, but it opened the door to a deeper understanding of the world. Ferrofluids are liquids that contain tiny magnetic particles. When you place a magnet near a ferrofluid, the liquid responds, forming spikes and patterns that seem almost alive. The particles inside align with the field, and the fluid reshapes itself to follow the field lines. It's a visible demonstration of invisible forces, a way to see magnetism in action. Ferrofluids are used in some loudspeakers, in seals for hard drives, and in experimental art. They're a bridge between science and beauty, showing us that the principles governing the universe can also be mesmerizing. The Earth's inner core, a solid sphere of iron and nickel about the size of the moon, rotates slightly faster than the rest of the planet. This differential rotation contributes to the generation of the magnetic field. The inner core is surrounded by the outer core, a churning sea of liquid metal, and together they form the geodynamo. The inner core is under immense pressure, so great that the metal remains solid despite temperatures as hot as the surface of the sun. It's a furnace at the center of the world, and it has been burning, in a sense, for billions of years. We live on a thin crust above this inferno, protected by distance, by rock, and by the magnetic field it creates. Some meteorites are magnetic. When they form in space, they can record the magnetic fields of the early solar system, or even of their parent bodies. By studying these meteorites, scientists can learn about the magnetic environments of asteroids and planets that no longer exist. It's like reading a letter from the past, written in stone and magnetism. These rocks have traveled for millions of years through the cold and silence of space, carrying their magnetic memories with them. When they land on Earth, they bring us a piece of that ancient story. Magnetic fields are also involved in the formation of planets. In the early solar system, a disk of gas and dust surrounded the young sun. Within this disk, magnetic fields help transport angular momentum, allowing material to spiral inward and clump together. Over time, these clumps grew into planets. Magnetism was one of the invisible hands shaping the architecture of our solar system. Without it, the planets might have formed differently, or not at all. It's a humbling thought that the ground beneath you, the air you breathe, the very existence of Earth, owes something to the quiet influence of magnetic fields. Even in the human body, there are tiny magnetic fields. Every time your heart beats, it generates a small electric current, and that current produces a faint magnetic field. The same is true for your brain. Neurons communicate using electrical signals, and those signals create magnetic fields that can be measured with sensitive instruments called magnetoencephalographs. These fields are incredibly weak, billions of times weaker than Earth's, but they are there. In a way, you are a magnetic being, a small, warm generator of invisible forces. And right now, as you rest, those fields are humming quietly within you, part of the symphony of life. The study of magnetism has a long and gentle history. In ancient China, people noticed that certain stones could attract iron, and they used them to create the first compasses. In ancient Greece, the philosopher Thales observed that lodestone could move iron filings, and he wondered if the stone had a soul. In the medieval Islamic world, scholars experimented with magnets and wrote treatises on their properties. In Europe, William Gilbert published De Magnete in 1600, proposing that the Earth itself was a giant magnet. Each generation added to the understanding, slowly, patiently, building a picture of the invisible world. And now, centuries later, we know so much more, yet the sense of wonder remains. Magnetism and electricity are two sides of the same force. In the 19th century, scientists discovered that a changing magnetic field can create an electric current, and a moving electric charge can create a magnetic field. This insight, captured in Maxwell's equations, unified two seemingly separate phenomena into one: electromagnetism. It was one of the great intellectual achievements of humanity, a moment when the universe revealed a deeper simplicity. And it all began with observations of magnets and wires, simple experiments conducted with care and curiosity. The speed of light itself is related to electricity and magnetism. Maxwell's equations predicted that electromagnetic waves should travel at a certain speed, and when that speed was calculated, it matched the speed of light. This led to the realization that light is an electromagnetic wave, a ripple in the electric and magnetic fields. Every photon of light that reaches your eyes is a tiny oscillation of these fields, traveling through space at the universe's speed limit. When you see the stars, you're seeing ancient light, ancient waves of electromagnetism, carrying information across the void. And in that light, there's magnetism woven into every ray. Auroras occur on other planets too. Jupiter and Saturn both have powerful auroras at their poles, driven by their strong magnetic fields and the charged particles in their magnetospheres. These auroras are much larger and more intense than Earth's, glowing in ultraviolet and infrared, as well as visible light. If you could stand on one of Jupiter's moons and look up, you might see a sky ablaze with colors we can barely imagine, a light show powered by the largest magnetic field in the solar system. It's a reminder that the phenomena we see on Earth are not unique, but part of a broader pattern, a universal language of magnetism and light. Even comets interact with magnetic fields. As a comet approaches the sun, it heats up and releases gas and dust, forming a glowing coma and a tail. The solar wind, carrying the sun's magnetic field, pushes on the ionized gas in the coma, creating a long, straight ion tail that always points away from the sun. The comet's path through space becomes visible because of this interaction, a delicate dance between ice, gas, and magnetism. Comets are ancient travelers, and they carry with them the memory of the early solar system, shaped and guided by invisible forces. There are places on Earth where the magnetic field is unusually strong or weak. These are called magnetic anomalies. Some are caused by large deposits of magnetic minerals in the crust. Others are remnants of ancient volcanic activity. The Kursk magnetic anomaly in Russia is one of the strongest, caused by a massive deposit of iron ore. The South Atlantic anomaly is a region where the magnetic field is weaker than average. allowing more radiation from the Van Allen belts to reach lower altitudes. Satellites passing through this region receive higher doses of radiation and sometimes experience glitches. But even these anomalies are part of the natural variation, the Earth's magnetic personality, expressed in stone and space. Magnetic fields can also influence the behavior of plasma. Plasma is the fourth state of matter, a hot, ionized gas where electrons are separated from atoms. Stars are made of plasma, and so is the solar wind. In plasma, magnetic fields can guide the motion of particles, creating structures like loops, filaments, and sheets. On the Sun, these structures are visible as prominences and coronal loops, arching high above the surface. In laboratories, scientists use magnetic fields to confine plasma in experimental fusion reactors, trying to recreate the conditions inside stars. It's a way of holding a piece of the sun in a bottle, using magnetism as the cage. The Earth's magnetic field extends far into space, forming a region called the magnetosphere. This is not a physical sphere, but a volume of space where the Earth's magnetic field dominates over the solar wind. The magnetosphere is shaped like a teardrop, compressed on the side facing the sun and stretched into a long tail on the night side. This tail can extend for millions of miles, far beyond the orbit of the moon. Within the magnetosphere, particles are trapped, guided, and accelerated. It's a dynamic, ever-changing environment, responding to the solar wind like a sail responds to the wind. And it's always there, surrounding the planet, a silent guardian. Some animals may use magnetic fields in ways we don't yet understand. There are reports of dogs and cats finding their way home over long distances. And while scent and memory likely play a role, magnetism might too. Cows and deer tend to align their bodies along magnetic field lines when they graze or rest, though the reason isn't clear. It might help them maintain a sense of direction, or it might be a vestigial behavior, a remnant of an ancient navigational system. We're still learning. The natural world is full of subtle connections, and magnetism is one of the threads that ties it all together. The concept of magnetic field lines is a human invention, a way of visualizing something invisible. The lines don't really exist. They're just a tool, a metaphor, but they're a useful one. By imagining lines that flow from north to south, curving through space, we can predict how magnets will behave, how compasses will point, how charged particles will move. These imaginary lines help us see the shape of the invisible, and in doing so, they reveal the order underlying the chaos. Science is full of such tools, ways of making the abstract tangible, the hidden visible. Magnetic fields are conservative in one sense. They don't do work on a charged particle moving through them. They can change the direction of the particle, bending its path into a curve or a spiral, but they don't change its speed. The particle's kinetic energy remains constant. This is why charged particles in a magnetic field move in circles or helices, spiraling endlessly unless another force intervenes. It's a kind of perpetual motion, though not the impossible kind. The particle is always moving, always turning, held in a gentle, invisible grip. There's a certain poetry to the fact that magnetic fields have no beginning and no end. Magnetic field lines always form closed loops. They emerge from the North Pole of a magnet and curve around to enter the South Pole, then continue through the interior of the magnet back to the North Pole. There are no magnetic monopoles, no isolated North or South poles, at least none that we've ever found. Every magnet, no matter how small, is a dipole, a pair. If you break a magnet in half, you don't get a north piece and a south piece. You get two smaller magnets, each with its own north and south. It's a fundamental symmetry, a rule the universe seems to follow without exception. The Earth's magnetic field is not static. It pulses and ripples in response to the solar wind. These fluctuations are called geomagnetic pulsations, and they occur on timescales ranging from fractions of a second to several minutes. Most of the time, they're too subtle to notice, but sensitive instruments can detect them. Some researchers have speculated that animals might sense these pulsations and use them as a kind of temporal signal, a way of keeping time or sensing changes in the environment. It's an open question, one of many that remain. Magnetic fields can also store energy. When you compress a magnetic field, you do work on it, and that work is stored as magnetic energy. This is what happens in a solar flare. The sun's magnetic field lines become twisted and tangled by the motion of the plasma. Energy builds up in the field like tension in a stretched rubber band. Eventually, the field reconfigures itself, releasing the stored energy in a sudden burst. This energy heats the plasma, accelerates particles, and sends light and matter streaming into space. It's a violent process, but it's also a release, a return to a lower energy state. The universe always seeks balance. Even the act of reading these words or listening to them involves magnetism. If you're using a device with a hard drive, the data is stored as tiny magnetic domains on a spinning disk. If you're using a solid-state drive, the data is stored as electric charges, but the principles of electromagnetism still apply. The screen you're looking at, if it's an LCD or LED, uses electric fields to control the light, and those fields are intimately connected to magnetism. The very technology that allows you to experience this moment is built on centuries of understanding magnetic and electric forces. It's a testament to human curiosity and to the quiet power of the invisible. Magnetism is ancient, but it's also timeless. The same principles that govern a lodestone govern a neutron star. The same force that guides a bird guides a spacecraft. From the smallest atom to the largest galaxy, magnetism is present, shaping, guiding, connecting. And tonight, as you rest, you're part of that continuum. The Earth's magnetic field passes through you, just as it passes through the birds and the turtles and the bacteria. You're held in the same invisible embrace that has held life on this planet for billions of years. There's something deeply comforting in that thought, isn't there? That we're all connected, all guided, all part of a larger pattern. The invisible architecture of magnetism extends into the smallest corners of life, reaching down into the bodies of bacteria that live in quiet waters and soft sediments. These tiny organisms, called magnetotactic bacteria, contain chains of magnetic crystals inside their cells. Each crystal is made of magnetite, the same mineral that ancient compasses were carved from. The bacteria use these internal magnets to orient themselves along Earth's magnetic field lines, swimming effortlessly toward the sediment, where oxygen is scarce and conditions suit them best. They do not think or choose. They simply follow the field, drifting downward in alignment with forces they cannot see, but perfectly obey. It is navigation at its most elemental, a biological compass no larger than a whisper. These magnetite crystals form in precise shapes, often as tiny octahedrons or elongated prisms, arranged in delicate chains like beads on a thread. The bacteria grow them with astonishing care, one crystal at a time, inside membrane-bound compartments called magnetosomes. The size and shape of each crystal are controlled so precisely that they function as perfect single-domain magnets, meaning each one holds its magnetic orientation without flipping or fading. This is engineering at the nanoscale, carried out by organisms with no brain, no blueprint, only the quiet instructions of genes refined over billions of years. When the bacterium dies, its magnetite crystals remain, settling into the sediment. Over time, layers of these microfossils accumulate, preserving a record of ancient magnetic fields in stone. Scientists have found magnetofossils in rocks more than 2 billion years old, suggesting that life has been interacting with Earth's magnetic field for an unimaginable span of time. These ancient crystals tell us that the geodynamo, was active long before animals walked on land, before forests grew, even before oxygen filled the atmosphere. The magnetic field has been a constant companion to life, shaping behaviors and evolutionary paths in ways we are only beginning to understand. It is humbling to think that something so invisible has been so influential, guiding microscopic swimmers through ancient seas, long before anything with eyes existed to see the sky. And magnetism is not confined to bacteria. Crystals of magnetite have been found in the tissues of many animals, including fish, sea turtles, lobsters, and even honeybees. In some species, these particles are located near nerve cells, suggesting they play a role in sensing the magnetic field. The exact mechanism is still debated, still studied, still wrapped in gentle mystery. But the presence of these crystals across so many branches of the tree of life suggests that magnetoreception, the ability to sense magnetic fields, is an ancient and widespread adaptation. It is a sense we humans lack, or have lost, or never needed. But for countless other creatures, it is as natural as sight or smell. Honeybees, for instance, appear to use magnetic information when building their hives. The wax combs they construct often align with geomagnetic directions, though the bees themselves seem unaware of this preference. It is an unconscious architecture, a subtle influence that shapes the geometry of their world. Researchers have placed magnets near hives and observed changes in comb orientation, confirming that bees are sensitive to magnetic fields. The crystals in their abdomens may act as tiny sensors, feeding information into their nervous systems in ways that guide construction, navigation, and perhaps even communication through the waggle dance. The hive hums with invisible geometry, its walls aligned not just by instinct, but by the planet's quiet pull. Lobsters, too, carry magnetite in their bodies and use Earth's field to navigate across the seafloor. They migrate seasonally, walking in long, single-file lines across sandy bottoms, sometimes traveling dozens of kilometers. Studies have shown that they can orient themselves even in complete darkness, even when currents and scents are stripped away. The magnetic field provides a stable reference, a map that does not fade with the tide. When researchers disrupted the local magnetic environment with artificial fields, the lobsters became disoriented, wandering without direction. Restore the field, and they resumed their journey. It is a reminder that orientation, for many creatures, is not just visual or chemical. It is also magnetic, woven into the body's silent knowledge of space. Salmon, those tireless travelers, also rely on magnetic cues to find their way home. After years in the open ocean, they return to the exact river where they were born, swimming upstream against powerful currents to spawn in the same gravel beds their parents once used. For decades, scientists wonder how they accomplished this feat. Smell plays a role, especially in the final stages. But in the open ocean, far from any coast, salmon use a combination of cues, and magnetism is among the most important. They imprint on the magnetic signature of their birthplace when they are young, memorizing the specific intensity and inclination of the field at that location. Years later, they use this memory as a coordinate, a magnetic address that guides them across thousands of kilometers of featureless water. Experiments have confirmed this. Researchers expose young salmon to artificial magnetic fields that mimic locations far from their actual birthplace. Years later, those fish attempted to return not to where they were born, but to the location represented by the magnetic field they had imprinted on. They followed a map written in invisible lines, a map more reliable than stars or currents. It is navigation by memory and magnetism, a partnership between biology and physics that allows life to traverse vast distances with quiet confidence. Sea turtles perform similar feats. Hatchlings emerge from eggs buried in sand, scramble toward the ocean, and disappear into the waves. For years, they drift and swim across entire ocean basins, riding currents, feeding, growing. Then, when they reach maturity, they return to the very beach where they were born to lay their own eggs. This journey can span decades and thousands of kilometers. How do they remember? How do they find their way back to a shoreline they left as tiny, fragile hatchlings? The answer lies partly in a magnetic map. Sea turtles appear to sense both the intensity and the inclination of Earth's magnetic field, and these two parameters vary predictably across the globe. Together, they create a grid, a coordinate system that allows turtles to determine their latitude and longitude without ever seeing the sun or stars. Young turtles learn this map as they drift, updating their internal sense of position as the magnetic field changes around them. When it is time to return, they reverse the journey, following magnetic gradients back to the region, and eventually the beach, that matches their earliest memory. It is a form of navigation so elegant, so refined, that engineers study it in hopes of improving human technologies. Even more remarkable, sea turtles can detect extraordinarily subtle variations in the magnetic field, differences as small as a fraction of percent. This sensitivity allows them to distinguish between locations that are relatively close together, fine-tuning their navigation as they approach their destination. It is as if they are reading the Earth's field with the precision of a surveyor, measuring invisible contours that guide them home. The mechanism likely involves magnetite crystals in their brains, though the exact neural pathways remain under investigation. What is clear is that the turtles are not guessing. They are reading, interpreting, and responding to information encoded in the planet's magnetic embrace. Birds, as we have touched upon, also navigate using magnetism, but the story grows richer the more closely we look. Some species, such as robins and European robins, rely not only on magnetite-based receptors, but also on a quantum mechanism involving molecules in their eyes. These molecules, called cryptochromes, are sensitive to the angle of magnetic field lines. When light strikes them, they enter a quantum state in which pairs of electrons become entangled, their spins correlated in ways that depend on the surrounding magnetic field. The presence of the field influences the chemical reactions that follow, and these reactions, in turn, send signals to the bird's brain. The bird does not see the magnetic field as a color or shape, but it perceives it nonetheless as a pattern of neural activity that corresponds to direction. This process is so delicate that it can be disrupted by very weak radio frequency electromagnetic fields, the kind produced by electronic devices. Studies have shown that migratory birds exposed to such interference lose their ability to orient correctly. Remove the interference, and their compass sense returns. It suggests that the quantum mechanism is extraordinarily sensitive, operating at the boundary between biology and fundamental physics. The bird's eye becomes a quantum sensor, a living instrument that measures the invisible geometry of space. What makes this even more astonishing is that the quantum states involved last only microseconds, yet they are stable enough to provide reliable information. Entangled electron pairs, flickering in and out of existence, guide journeys that span continents. It is a reminder that life does not only adapt to the large and obvious forces of nature, it also learns to listen to the subtle, the fleeting, the quantum whisper. And in doing so, it achieves feats of navigation that rival any technology we have devised. Beyond individual organisms, magnetism shapes entire ecosystems in quiet, indirect ways. Coral reefs, for instance, grow in patterns influenced by the flow of ocean currents, and those currents are themselves shaped by Earth's magnetic field through a process called magnetohydrodynamics. When seawater, which contains dissolved salts and is therefore electrically conductive, moves through a magnetic field, it generates weak electric currents. These currents, in turn, interact with the magnetic field to create forces that subtly alter the flow of water. The effect is small, but over time and across vast distances, it contributes to the circulation patterns that distribute heat, nutrients, and larvae throughout the ocean. Coral larvae drifting in these currents are carried to new locations, where they settle and grow, building reefs that become havens for countless species. The magnetic field also influences the distribution of nutrients in the ocean by affecting the movement of charged particles in seawater. Iron, an essential nutrient for phytoplankton, can exist in forms that are influenced by electromagnetic forces. In some regions, the interplay between ocean currents, magnetic fields, and nutrient chemistry creates conditions that favor blooms of phytoplankton, the microscopic plants that form the base of the marine food web. These blooms feed zooplankton, which feed fish, which feed larger predators, all the way up the chain. The magnetic field, though invisible and often forgotten, is part of the web of relationships that sustains life in the sea. On land, the magnetic field plays a subtler role, but one no less important. It shields the surface from cosmic rays and solar particles, as we have discussed, but it also influences the chemistry of the atmosphere in ways that affect weather and climate. High-energy particles from space collide with molecules in the upper atmosphere, creating ions and free radicals that participate in chemical reactions. These reactions can influence the formation of clouds, the concentration of ozone, and the distribution of trace gases. The connections are complex and still being studied, but it is becoming clear that the magnetic field is not just a passive shield. It is an active participant in the processes that shape our environment. There is even evidence that changes in Earth's magnetic field, such as reversals or excursions, may correlate with shifts in climate and biodiversity. During periods when the field weakens, more cosmic rays reach the atmosphere, potentially increasing cloud cover and altering temperature patterns. Some researchers have proposed that these changes could trigger ice ages or influence the timing of evolutionary events. The evidence is still debated, still tentative, but the possibility is intriguing. It suggests that the magnetic field is not just a backdrop to life's story, but a character in it, shaping the stage on which evolution unfolds. Rocks, too, carry the memory of ancient magnetic fields, and they do so with a patience that outlasts mountains. When lava cools and solidifies, the magnetic minerals within it align with Earth's field at that moment, freezing a record of the field's direction and intensity. This process, called thermoremnant magnetization, turns every volcanic rock into a tiny archive. By studying these rocks, scientists can reconstruct the history of Earth's magnetic field over millions of years, tracing its reversals, its wanderings, its moments of weakness and strength. The rocks do not forget. They hold their secrets quietly, waiting for someone to read them. Sedimentary rocks also record magnetic information, though in a different way. As particles settle slowly to the bottom of lakes or oceans, magnetic grains among them align with the field before they are buried and compacted into stone. This process, called depositional remnant magnetization, is gentler than the volcanic version, but it is no less valuable. It allows scientists to study the magnetic field's behavior during times when volcanic activity was rare, filling in gaps in the record. Together, volcanic and sedimentary rocks provide a continuous history of the geodynamo, stretching back billions of years. This history reveals that the magnetic field is not static. It drifts, fluctuates, and occasionally flips, with the north and south magnetic poles exchanging places. These reversals happen irregularly, sometimes after a few 100,000 years, sometimes after tens of millions. The last reversal occurred about 780,000 years ago, and we are overdue for another, though overdue is a human concept that the planet does not recognize. The field does not operate on a schedule. It follows the chaotic rhythms of the outer core, responding to currents and instabilities that we can model but not predict with certainty. During a reversal, The field does not simply flip overnight. It weakens, becomes disorganized, and may develop multiple poles scattered across the globe. This transition can take thousands of years, during which the field's strength may drop to a fraction of its normal value. The magnetosphere shrinks, allowing more cosmic rays and solar particles to reach the atmosphere. Auroras might appear at lower latitudes, shimmering over regions that normally never see them. Navigation for animals could become more difficult, though life has survived many reversals in the past, suggesting that organisms are more resilient or more adaptable than we might fear. There is no evidence that reversals cause mass extinctions, though some studies have suggested weak correlations with changes in biodiversity. The truth is that life is tough, and the magnetic field, even when weak, still provides some protection. The atmosphere itself also shields the surface from radiation, and the ozone layer absorbs much of the harmful ultraviolet light from the sun. A reversal would be a challenge, certainly, but not a catastrophe. It would be a slow, strange time, a time when compasses would spin and auroras would dance in unfamiliar skies. But the world would continue, and life would adapt, as it always has. The study of these reversals has led to one of the most important discoveries in geology, the theory of plate tectonics. In the mid-20th century, scientists mapping the magnetic properties of the ocean floor noticed something extraordinary. The rocks on either side of mid-ocean ridges showed alternating bands of normal and reversed magnetic polarity, like stripes on a zebra. These stripes were symmetrical, mirroring each other across the ridge. The only explanation was that new ocean floor was being created at the ridge, spreading outward as magma rose from below and cooled. As each new strip of rock formed, it recorded the magnetic field's orientation at that time. When the field reversed, the next strip recorded the opposite polarity. The pattern was a tape recorder, playing back the history of the geodynamo, and, in doing so, revealing the motion of the continents. This discovery transformed our understanding of the planet. It showed that Earth's surface is not fixed, but dynamic, with plates of crust drifting slowly across the mantle, colliding, separating, and sliding past one another. Mountains rise where plates collide. Ocean basins open where they pull apart. Earthquakes and volcanoes mark the boundaries where plates meet. And all of this motion, this grand, slow dance of continents, was revealed by studying the magnetic stripes on the ocean floor. Magnetism, once again, proved to be a guide, a teacher, a key to unlocking the planet's deepest secrets. The mid-ocean ridges themselves are places of quiet creation. Magma wells up from the mantle, cools, and solidifies, forming new crust at a rate of a few centimeters per year. It is a process so slow that no human lifetime could witness significant change. Yet over millions of years, it reshapes the face of the planet. The Atlantic Ocean, for instance, is widening, pushing the Americas away from Europe and Africa. The Pacific Ocean is shrinking as its edges are consumed by subduction zones, where old crust sinks back into the mantle. The Mediterranean Sea is closing, and one day, tens of millions of years from now, Africa will collide with Europe, raising new mountains where the sea once was. All of this motion is driven by convection in the mantle, the same process that powers the geodynamo. The planet is a system of interlocking cycles, each one influencing the others, each one written in the language of heat, motion, and magnetism. Even the moon, our silent companion, plays a role in this story, though not in the way you might expect. The moon no longer has a magnetic field, but it once did. Rocks brought back by Apollo astronauts contain magnetic minerals that are magnetized, indicating that a dynamo once operated in the moon's core. This dynamo likely shut down billions of years ago as the moon cooled and its core solidified. The loss of the field left the moon vulnerable to the solar wind, which has been slowly stripping away its thin atmosphere ever since. Today, the moon's surface is a barren, airless desert, scarred by impacts and bathed in radiation. It is a reminder of what can happen when a magnetic field fades, though the moon's small size and lack of atmosphere meant it had little to lose. Some of the moon's rocks show surprisingly strong magnetization, stronger than would be expected from the moon's weak gravity and small core. One hypothesis is that the early moon experienced impacts so powerful that they generated transient magnetic fields, lasting only hours or days, but intense enough to magnetize nearby rocks. These impact-generated fields would have been created by the vaporization and ionization of rock, which, moving rapidly through space, could have acted like a temporary dynamo. It is a strange and violent process, a reminder that magnetism can arise not only from the slow churn of a planet's core, but also from sudden, catastrophic events. Mars, too, once had a global magnetic field, but it disappeared roughly 4 billion years ago. Without it, the solar wind has been eroding Mars's atmosphere ever since, stripping away water vapor and other gases. This loss likely transformed Mars from a world with rivers and lakes into the cold, dry desert we see today. However, Mars still retains patches of strong magnetic field in its ancient crust, especially in the southern highlands. These regions are called magnetic anomalies, and they are some of the strongest crustal magnetic fields in the solar system. They are remnants of the time when Mars had a dynamo, frozen into the rocks like fossils of a lost era. Spacecraft orbiting Mars have mapped these anomalies in detail, revealing patterns that hint at ancient tectonic activity long since ceased. The presence of these crustal fields has implications for the possibility of life on Mars. Magnetic fields can create local protective zones, mini magnetospheres that shield small regions from the solar wind. If life ever existed on Mars, or if microbial life persists today in subsurface environments, these magnetic anomalies might offer some protection. It is a tenuous hope, but one that adds another layer to the story of magnetism and life. Even a dead dynamo leaves behind echoes, and those echoes might matter. Jupiter's magnetic field, as we have noted, is the strongest in the solar system, but it also exhibits fascinating dynamics. The field is not perfectly stable. It wobbles and shifts, and measurements from spacecraft visiting Jupiter decades apart have shown that the field structure changes over time. This suggests that Jupiter's dynamo is highly active, with currents in the metallic hydrogen ocean swirling and reorganizing on timescales of years to decades. It is a reminder that magnetic fields, even those of giant planets, are not static monuments. They are living processes, constantly evolving in response to the motions of the fluids that generate them. Jupiter's field also interacts with its moons in unexpected ways. Ganymede, as mentioned, has its own magnetic field, and when it orbits through Jupiter's magnetosphere, the two fields interact, creating complex patterns of electric currents and auroras on both bodies. Europa and Io, though they lack their own dynamos, generate induced magnetic fields as they move through Jupiter's field. The changing magnetic environment induces electric currents in their subsurface oceans or molten interiors, and these currents produce secondary magnetic fields that can be detected by spacecraft. This technique has been used to confirm the presence of a subsurface ocean on Europa, a discovery with profound implications for the search for life beyond Earth. Saturn's magnetic field is weaker than Jupiter's, but it has its own peculiarities. The field is almost perfectly aligned with Saturn's rotation axis, which is unusual. Most planets, including Earth, have magnetic fields that are tilted relative to their spin. Saturn's alignment suggests something unique about the structure or dynamics of its interior, something scientists are still working to understand. The field also interacts with Saturn's rings and moons, creating faint auroras, and influencing the distribution of charged particles in the magnetosphere. Enceladus, one of Saturn's moons, ejects plumes of water vapor from its south pole, and these plumes feed material into Saturn's magnetosphere, creating a torus of plasma that orbits the planet. The interaction between a magnetic field and this plasma generates radio waves that can be detected from Earth, a kind of cosmic music born from ice and magnetism. Uranus and Neptune, the ice giants, have magnetic fields that are wildly tilted and offset from their centers. Uranus's field is tilted about 60 degrees from its rotation axis, and Neptune's is tilted about 47 degrees. Both fields are also shifted significantly away from the planet's center, suggesting that they are not generated in a deep core, but rather in a layer of slushy, electrically conductive material closer to the surface. This material is thought to be a mixture of water, methane, and ammonia, compressed and heated until it becomes ionized and capable of conducting electricity. The dynamos in these planets are unlike anything we see elsewhere in the solar system, and they challenge our understanding of how magnetic fields can be generated. They are reminders that nature is more inventive than our theories, more diverse than our models. The offset and tilted fields of Uranus and Neptune create magnetospheres that are chaotic and asymmetric. As the planets rotate, their magnetic poles sweep through space, creating a corkscrew pattern that constantly changes the environment around them. Any moons or rings orbiting these planets experience rapidly varying magnetic conditions, a dynamic environment unlike the relatively stable magnetospheres of Earth or Jupiter. It is a strange and turbulent place, a reminder that magnetic fields can take many forms, each one shaped by the unique conditions of the body that generates it. Even smaller bodies, such as asteroids, can carry magnetic signatures. Some meteorites, fragments of asteroids that have fallen to Earth, contain magnetized minerals. This indicates that their parent bodies once had magnetic fields, generated either by dynamos and molten cores or by external fields during their formation. The presence of these fields suggests that the early solar system was a more magnetically active place than we might have imagined, with small bodies generating or recording fields as they collided, melted, and cooled. Each meteorite is a messenger, carrying information about conditions billions of years ago, written in the orientation of tiny magnetic grains. One particularly interesting class of meteorites, called carbonaceous chondrites, contains organic molecules and water, along with magnetic minerals. These meteorites are thought to be some of the most primitive materials in the solar system, largely unchanged since the solar nebula collapsed to form the Sun and planets. The magnetic grains in these meteorites may have been magnetized by the magnetic field of the early Sun, or by fields generated in the swirling disk of gas and dust that surrounded it. By studying these grains, scientists can learn about the magnetic environment of the solar nebula, the birthplace of our world. It is a form of archaeology conducted not with shovels, but with microscopes and magnetometers, reading the faint signatures left in stone. The Sun's magnetic field, as we have touched upon, is the source of much of the magnetic activity in the solar system. But the Sun is not unique. Every star generates a magnetic field, and the strength and behavior of that field depend on the star's size, age, and rotation rate. Young stars, which rotate rapidly, often have very strong magnetic fields and are highly active, with frequent flares and powerful stellar winds. As stars age and slow down, their magnetic activity typically decreases. Old stars, rotating slowly, have weaker fields and quieter surfaces. Our Sun is middle-aged, and its activity level is moderate, though it still produces flares and coronal mass ejections that can affect Earth. Some stars, called magnetic stars or AP stars, have fields thousands of times stronger than the Sun's. These fields are thought to be remnants of the star's formation, trapped and amplified as the star contracted. The strong fields affect the star's atmosphere, creating chemical peculiarities and surface spots that move as the star rotates. Observing these stars helps astronomers understand the role of magnetism in stellar evolution, and it provides a glimpse of the diversity of magnetic phenomena in the universe. Neutron stars, the collapsed cores of massive stars that have exploded as supernovae, have the strongest magnetic fields known. A typical neutron star has a field about 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, have field 1,000 times stronger still, reaching intensities that warp the very fabric of space around them. These fields are so powerful that they affect the behavior of atoms, stretching electron clouds into elongated shapes and altering the energy levels of atomic transitions. Near a magnetar, the vacuum itself becomes birefringent, meaning that light traveling through it splits into two polarizations that move at different speeds. It is a regime of physics where quantum mechanics and general relativity meet, a place where our everyday intuitions break down completely. Magnetars are rare, but they are also among the most violent objects in the universe. The intense magnetic fields store enormous amounts of energy, and occasionally, this energy is released in sudden bursts. The star's crust cracks, and magnetic field lines snap and reconnect, releasing energy in the form of X-rays and gamma rays. These bursts, called magnetar flares, can outshine entire galaxies for a fraction of a second. The largest flare ever observed, in 2004, came from a magnetar about 50,000 light-years away. It released more energy in 1/10 of a second than the Sun emits in 100,000 years. The radiation was so intense that it affected Earth's ionosphere, even from that vast distance. It was a reminder that magnetism, at its most extreme, is not gentle. But here, in this quiet moment, we can appreciate it from afar, safe and small, marveling at the forces that shape the cosmos. The magnetic field of our galaxy itself forms a quiet architecture that spans thousands of light years, threading through the spiral arms like invisible filaments of order in the cosmic dark. Radio telescopes detect these galactic magnetic fields by observing the way they twist the polarization of light from distant stars and nebulae. The field strength is extraordinarily weak compared to a refrigerator magnet. Yet across such vast distances, these gentle forces shape the flow of interstellar gas and influence where new stars are born. It is a slow choreography, unfolding over millions of years, written in lines of force that curve and loop through the emptiness between the stars. The Milky Way's magnetic field may have originated in the early universe, seeded by tiny fluctuations in the plasma that filled space shortly after the Big Bang. As galaxies formed and began to rotate, those faint seeds were stretched and amplified by a process called the dynamo effect, the same mechanism that powers Earth's magnetic field, but operating on a scale almost beyond comprehension. Rotation and turbulence in the galactic disk twist and fold the field lines, sustaining the magnetism across billions of years. It is a testament to the patience of nature, building structure slowly, quietly, without haste. Astronomers map the galaxy's magnetic field by studying pulsars, those rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. As the radio waves travel through space, they pass through regions of magnetized plasma, and their polarization rotates in a measurable way. By observing many pulsars scattered across the sky, scientists can reconstruct the three-dimensional structure of the galactic magnetic field, revealing its spirals and reversals. It is detective work on the grandest scale, piecing together an invisible map from whispers of light that have traveled for thousands of years. In the spaces between galaxies, magnetic fields persist even in the near emptiness of intergalactic voids. These fields are astonishingly weak, millions of times fainter than Earth's field. Yet they exist, woven into the tenuous gas that drifts in the vast dark. Their origin is still debated. They may have been ejected from galaxies by supernova-driven winds, or they may be primordial, relics from the universe's infancy. Either way, they remind us that magnetism is truly universal, present even in the loneliest corners of the cosmos. Magnetic fields also play a role in the mysterious phenomenon of cosmic ray acceleration. Charged particles, mostly protons, are flung to nearly the speed of light by shock waves from supernovae, and magnetic fields trap and scatter these particles, bouncing them back and forth until they gain tremendous energy. This process, called Fermi acceleration, turns ordinary particles into cosmic rays that zip through the galaxy and occasionally strike Earth's atmosphere. The magnetic field acts as both cage and catapult, holding the particles long enough to energize them, then releasing them into the void. Some of the most energetic cosmic rays come from beyond our galaxy, and their arrival directions are scrambled by the magnetic fields they pass through on their journey. This makes it difficult to trace them back to their sources, as if the universe has gently shuffled the evidence. But by studying the distribution and energy of these particles, scientists can learn about the magnetic environments they traversed. Each cosmic ray is a tiny messenger, carrying information encoded in its trajectory, and the magnetic fields of the universe are the medium through which that message is written. Within our own solar system, the sun's magnetic field extends far beyond the planets, forming a vast bubble called the heliosphere. This magnetic cocoon shields us from some of the galactic cosmic rays, deflecting and slowing them before they reach the inner planets. The boundary of the heliosphere, called the heliopause, is where the solar wind finally meets the interstellar medium, and the magnetic field there is complex and turbulent. The Voyager spacecraft crossed this boundary and sent back data showing a region of compressed, twisted magnetism, a frontier where two magnetic realms meet and mingle. The sun's magnetic field also creates structures called coronal loops, which arc high above the solar surface, glowing in ultraviolet and X-ray light. These loops are filled with hot plasma that follows the magnetic field lines, tracing their elegant curves. Sometimes these loops remain stable for days, gently glowing in the solar atmosphere. Other times they become unstable and erupt, releasing energy in solar flares or coronal mass ejections. But even in their quiet moments, they are beautiful, a visible manifestation of invisible forces drawn in light against the darkness of space. Closer to home, Earth's magnetosphere interacts with the solar wind in a dynamic, ever-changing dance. On the side facing the sun, the magnetosphere is compressed, pushed inward by the pressure of the solar wind. On the night side, it stretches out into a long tail called the magnetotail, extending far beyond the moon's orbit. This tail stores magnetic energy, and occasionally it releases that energy in a process called magnetic reconnection, which sends particles streaming back toward Earth and powers the auroras. It is a cycle of tension and release, playing out silently in the space around our planet. The magnetotail is not a simple structure, but a complex region with multiple layers and currents. There is a thin sheet of electric current running down its center, separating magnetic field lines that point in opposite directions. When these oppositely directed fields come together, they can reconnect, snapping into a new configuration and releasing energy in a sudden, quiet burst. This reconnection is one of the fundamental processes in plasma physics, occurring not only in Earth's magnetotail, but also on the Sun, in distant stars, and in the accretion disks around black holes. It is a universal phenomenon, a way that magnetic fields rearrange themselves and convert stored energy into motion and heat. Auroras themselves are not only visual spectacles, but also sources of sound, though the sounds are rare and subtle. In certain conditions, when the aurora is particularly strong and low in the atmosphere, people have reported hearing faint crackling or whooshing noises. The exact mechanism is still debated, but it may involve the discharge of static electricity from objects on the ground, triggered by rapid changes in the electric field associated with the aurora. These sounds are fleeting and delicate, a whisper accompanying the silent light show overhead, a reminder that the aurora is not just an image, but a physical presence in the air. The colors of the aurora depend on which atmospheric gases are being excited and at what altitude. Green, the most common color, comes from oxygen atoms about 100 kilometers up, glowing as they return to their ground state after being energized by incoming electrons. Red auroras, rarer and often seen at higher altitudes, also come from oxygen, but from a different transition that takes longer to emit light. Blue and purple hues come from nitrogen, adding variety to the display. Each color is a signature, a fingerprint of the atoms and molecules in our atmosphere, painted by the energy delivered from space. Sometimes the aurora takes the form of discrete arcs, stretching across the sky like curtains hung from an invisible ceiling. Other times it appears as diffuse patches or pulsating glows, shifting and breathing with a slow rhythm. The shapes and motions are determined by the structure of the magnetic field and the distribution of incoming particles. Watching an aurora is like watching the magnetic field made visible, its lines and flows translated into light. It is a rare gift, a chance to see the invisible architecture that surrounds our planet. In the polar regions, where auroras are most common, indigenous peoples have long woven them into their stories and traditions. Some cultures saw the lights as spirits of ancestors dancing in the sky. Others believed they were reflections from the sea, or torches held by beings guiding the dead to the afterlife. These stories, while not scientific, reflect a deep human response to the mystery and beauty of the aurora, a recognition that something profound and otherworldly is taking place. Science has given us the mechanism, but the sense of wonder remains unchanged. The study of auroras has also led to advances in understanding space weather, the conditions in space that can affect technology and infrastructure on Earth. Strong geomagnetic storms, driven by solar activity, can induce currents in power grids, damage satellites, and disrupt communication systems. By monitoring the solar wind and the state of Earth's magnetosphere, scientists can now forecast space weather with increasing accuracy, providing warnings that allow operators to take protective measures. It is a practical application of magnetism, using knowledge of invisible fields to safeguard the systems we depend on. Earth's magnetic field also plays a role in the formation of the Van Allen radiation belts, regions of space where charged particles are trapped and concentrated. These belts were discovered in 1958 by instruments aboard the Explorer 1 satellite, and they revealed that the space around Earth is not empty, but filled with energetic particles held in place by the magnetic field. The inner belt contains mainly protons, while the outer belt is dominated by electrons. These particles spiral along magnetic field lines, bouncing back and forth between the northern and southern hemispheres, confined by the magnetic mirror effect. The radiation belts pose a hazard to spacecraft and astronauts, as the energetic particles can damage electronics and harm living tissue. Understanding the belt structure and variability is essential for planning space missions and designing protective shielding. The belts also change in response to solar activity, swelling and contracting as the solar wind buffets the magnetosphere. They are a dynamic, living part of Earth's magnetic environment, constantly shifting in response to forces from the sun. Occasionally, a third, temporary radiation belt appears between the inner and outer belts, lasting for weeks before dissipating. This transient belt was discovered only recently, thanks to the Van Allen probe's mission, which provided detailed measurements of the radiation environment. The formation and decay of this third belt are still being studied, but it appears to be related to the way magnetic field lines are reconfigured during geomagnetic storms. It is a reminder that even in our own backyard, there are still surprises, still phenomena waiting to be understood. Beyond Earth, other planets with magnetic fields also have radiation belts. Jupiter's belts are far more intense than Earth's, filled with particles accelerated to extreme energies by the planet's rapid rotation and powerful magnetic field. Saturn, Uranus, and Neptune also have radiation belts, each with unique characteristics shaped by the planet's magnetic field and its interaction with the solar wind and any nearby moons. Studying these belts helps scientists understand the diversity of magnetic environments in the solar system and the fundamental physics that governs them. Magnetic fields also influence the atmospheres of planets in subtle ways. On Earth, the magnetic field helps protect the atmosphere from being stripped away by the solar wind, a process called atmospheric erosion. Mars, which lost its global magnetic field billions of years ago, has since lost much of its atmosphere, leaving it cold and thin. The solar wind, no longer deflected by a strong magnetic field, has gradually stripped away lighter gases, especially hydrogen. This slow loss has transformed Mars from a potentially warmer, wetter world into the dry, barren planet we see today. Venus, despite lacking a strong intrinsic magnetic field, has managed to retain a thick atmosphere, though for different reasons. Its proximity to the Sun means it receives more intense solar wind, but its atmosphere is so dense that it creates its own interaction with the solar wind, forming an induced magnetosphere. This is not as effective as a true magnetic field at shielding the atmosphere, and Venus does lose some atmospheric material to space, but the planet's volcanic activity may replenish the atmosphere over time. It is a different kind of balance, shaped by the absence of a protective magnetic field. The study of planetary magnetic fields extends to exoplanets, worlds orbiting distant stars. While we cannot yet directly measure the magnetic fields of exoplanets, scientists can infer their presence from certain observations. For example, some hot Jupiters, gas giants orbiting very close to their stars, may have strong magnetic fields that interact with the stellar wind, producing radio emissions. Detecting these emissions would confirm the presence of a magnetic field and provide clues about the planet's interior and rotation. It is a frontier of research, using magnetism as a tool to explore worlds we cannot yet visit. Magnetic fields also affect the habitability of planets. A strong magnetic field can protect a planet's atmosphere and surface from harmful radiation, creating a more stable environment for life. Earth's magnetic field has likely played a role in making our planet habitable, shielding the atmosphere from erosion and deflecting high-energy particles that could damage living cells. When scientists search for potentially habitable exoplanets, the presence of a magnetic field is considered an important factor, though not the only one. It is part of the complex web of conditions that make a world suitable for life. Some researchers have even suggested that magnetic fields could be detected around exoplanets by observing how they affect the stellar wind. If a planet has a strong magnetic field, it will carve out a cavity in the stellar wind, creating a bow shock similar to Earth's magnetopause. This interaction could produce observable signatures in the star's spectrum or in the radio emissions from the system. It is a challenging observation, requiring sensitive instruments and careful analysis, but it represents a way to study the magnetic properties of distant worlds. On Earth, the magnetic field has influenced the evolution of life in ways that are still being explored. Some organisms, as we have seen, use the magnetic field for navigation, but there may be other, subtler effects. For example, the magnetic field helps protect the ozone layer by deflecting charged particles that could otherwise break down ozone molecules. The ozone layer, in turn, shields the surface from harmful ultraviolet radiation, making it safer for life to thrive on land. In this way, the magnetic field has an indirect but important role in shaping the conditions for life. There is also evidence that changes in Earth's magnetic field, such as reversals or excursions, may have influenced evolutionary history. During a reversal, when the field weakens, more cosmic rays reach the atmosphere, potentially increasing mutation rates and affecting climate through changes in cloud formation. Some researchers have looked for correlations between magnetic reversals and mass extinctions, or evolutionary radiations, though the evidence is still debated. It is a fascinating area of study, linking the deep interior of the planet to the history of life on its surface. The magnetic field also leaves its mark on human history in subtle ways. Ancient navigators used lodestones, naturally magnetized pieces of magnetite, as primitive compasses, allowing them to travel across open seas and vast deserts. The magnetic compass, refined over centuries, became one of the most important tools of exploration and trade, enabling the age of discovery and the mapping of the world. In this way, the invisible force of magnetism helped shape the course of human civilization, guiding travelers and connecting distant cultures. Even today, the magnetic field continues to guide us, not only through compasses but through the sophisticated navigation systems in our phones and vehicles. GPS satellites provide precise location data, but magnetic sensors help determine orientation and heading, especially when GPS signals are weak or unavailable. The ancient force of magnetism, harnessed by modern technology, remains a quiet companion in our daily lives, helping us find our way without fanfare or drama. The study of magnetism has also led to technological innovations beyond navigation. Magnetic resonance imaging, or MRI, uses powerful magnetic fields and radio waves to create detailed images of the inside of the human body. The technique relies on the magnetic properties of hydrogen atoms in water and fat, which align with the external field and then emits signals as they relax. MRI has revolutionized medicine, allowing doctors to see soft tissues, organs, and the brain with remarkable clarity, all without using ionizing radiation. It is a peaceful application of magnetism, healing rather than harming. Magnetism also plays a role in data storage, from the magnetic tapes of the past to the hard drives in modern computers. Information is encoded as patterns of magnetization on a spinning disk, read and written by tiny magnetic heads. Though solid-state drives are becoming more common, magnetic storage remains widespread, quietly preserving our data in the language of aligned and unaligned magnetic domains. It is a reminder that the same force that guides birds and powers auroras also stores our memories, our music, our knowledge. In the realm of quantum physics, magnetism takes on even stranger and more subtle forms. Electrons have a property called spin, which gives them a tiny magnetic moment, making each electron a miniature magnet. In most materials, these spins are randomly oriented, and their magnetic effects cancel out. But in ferromagnetic materials, the spins align, creating a macroscopic magnetic field. Understanding and controlling electron spin is at the heart of spintronics, a field of research that aims to use spin, rather than charge, to carry and process information. It is a quiet revolution, exploring the magnetic properties of matter at the smallest scales. Magnetic fields also appear in the quantum phenomenon of superconductivity, where certain materials lose all electrical resistance when cooled below a critical temperature. Superconductors expel magnetic fields from their interior, a phenomenon called the Meissner effect. If you place a magnet above a superconductor, it will levitate, held aloft by the repulsion of the magnetic field. This levitation is silent, stable, and almost magical in appearance, a visible demonstration of quantum mechanics at work. It is a calming image, the magnet floating effortlessly, suspended by invisible forces. Superconducting magnets are used in many applications, from MRI machines to particle accelerators. where they generate powerful, stable magnetic fields without the energy loss of conventional electromagnets. The magnets must be kept extremely cold, often using liquid helium, but the result is a magnetic field of extraordinary strength and uniformity. These magnets are marvels of engineering, harnessing quantum effects to create fields far stronger than those found naturally on Earth. They are tools of science, enabling discoveries in physics, chemistry, and medicine. In the natural world, magnetic fields also play a role in the behavior of certain minerals and rocks. Lodestone, the naturally magnetized form of magnetite, has been known since ancient times and was used in early compasses. The magnetization occurs when lightning strikes rocks containing magnetite, or when the rocks cool in the presence of Earth's magnetic field, locking in a permanent magnetization. These natural magnets are rare and treasured, small pieces of the Earth that carry a memory of the planet's magnetic field at the time they formed. Some rocks also exhibit a property called remnant magnetization, where they retain a record of the magnetic field that was present when they solidified. This is the basis of paleomagnetism, the study of ancient magnetic fields recorded in rocks. By analyzing the direction and intensity of remnant magnetization, scientists can reconstruct the history of Earth's magnetic field, including the timing and duration of past reversals. It is a form of time travel, reading the magnetic memories stored in stone, layer by layer, era by era. Certain sediments also record the magnetic field, as tiny magnetic grains settle and align with the field before being locked in place by the accumulating sediment. Lake beds and ocean floors preserve a continuous record of magnetic field variations, sometimes spanning millions of years. These records have revealed the irregular rhythm of magnetic reversals and the slow drift of the magnetic poles. They are archives of the planet's magnetic history, written in the quiet accumulation of particles at the bottom of ancient seas. The magnetic properties of rocks have also been used to study the movement of continents. As tectonic plates drift, the rocks they carry preserve the magnetic field direction at the time of their formation. By comparing the magnetic orientations of rocks from different continents, scientists can reconstruct how the continents were once joined and how they have moved over time. This was one of the key pieces of evidence supporting the theory of plate tectonics, showing that the continents are not fixed, but slowly wander across the surface of the Earth, guided by forces deep below. In the deep ocean, hydrothermal vents release hot, mineral-rich water from the seafloor, and some of the minerals precipitated at these vents are magnetic. Magnetite and other iron-rich minerals form chimneys and mounds around the vents, and these structures record the magnetic field at the time of their formation. Studying these magnetic minerals helps scientists understand the chemistry and temperature of the vent fluids, as well as the history of volcanic activity on the seafloor. It is geology written in magnetism, a record of the dynamic processes that shape the ocean floor. Magnetic fields also influence the behavior of plasmas in laboratory experiments, where scientists study fusion energy and other high-temperature phenomena. In a fusion reactor, powerful magnetic fields confine the hot plasma, preventing it from touching the walls of the reactor and cooling down. The magnetic confinement is essential for sustaining the conditions needed for fusion, where atomic nuclei merge and release energy. It is a delicate balance, using invisible forces to hold a miniature star in place, a controlled dance of magnetism and matter. The study of magnetic confinement has led to the development of devices like tokamaks and stellarators, which use complex magnetic field geometries to trap and heat plasma. These machines are marvels of engineering, with superconducting magnets generating fields strong enough to hold plasma at temperatures hotter than the core of the sun. The goal is to achieve sustained fusion, a clean and virtually limitless source of energy. It is a long-term endeavor, requiring patience and precision, but the potential rewards are immense. Magnetism, once again, is at the heart of the effort. In the natural world, Magnetic fields also appear in the phenomenon of magnetic bacteria, which we touched on earlier, but their story goes deeper. These bacteria contain chains of magnetite crystals called magnetosomes, which act like tiny compass needles. The bacteria use these magnetosomes to orient themselves along magnetic field lines, swimming toward regions of lower oxygen concentration in sediments. This behavior, called magnetotaxis, is an elegant solution to the problem of navigation in a murky, three-dimensional environment. The bacteria do not see or sense oxygen directly. They simply follow the magnetic field, which happens to point in the right direction. The magnetosomes are not just random crystals, but are carefully controlled in size, shape, and arrangement by the bacteria. Each crystal is enclosed in a membrane and organized into a chain, maximizing the magnetic moment and ensuring that the bacteria respond efficiently to the magnetic field. This level of control suggests that magnetotaxis is an ancient and highly refined adaptation, possibly dating back billions of years. It is a quiet marvel of biological engineering, invisible to the naked eye, but exquisitely functional. Some researchers have even found magnetotactic bacteria in both the northern and southern hemispheres. And interestingly, the bacteria in each hemisphere swim in opposite directions along the magnetic field lines. In the northern hemisphere, they swim north and downward, while in the southern hemisphere, they swim south and downward. This is because the magnetic field lines point downward in both regions, toward the poles. The bacteria are not navigating toward a compass direction, but toward the sediment, using the magnetic field as a reliable guide. It is a beautiful example of how life adapts to the local magnetic environment. Magnetotactic bacteria have also inspired biotechnology, with scientists exploring ways to use magnetosomes for medical imaging and drug delivery. The magnetite crystals are biocompatible and can be guided using external magnetic fields, making them potentially useful for targeting specific tissues or cells in the body. It is an area of active research, translating the natural magnetism of bacteria into tools for human health. Nature, once again, provides the blueprint, and we're learning to read it. The magnetic fields of stars, too, continue to reveal their secrets. Sunspots, those dark patches on the sun's surface, are regions of intense magnetic field, thousands of times stronger than Earth's field. The strong magnetism inhibits the convection of hot gas from the interior, cooling the surface and making the sunspot appear darker. Sunspots come and go in an 11-year cycle, reflecting the periodic reversal of the sun's magnetic field. At solar maximum, the sun is covered with sunspots in active regions. At solar minimum, the surface is calm and nearly spotless. It is a slow, steady rhythm driven by the dynamo deep inside the sun. The sun's magnetic field also extends into space, carried by the solar wind, and it takes the form of a spiral pattern called the Parker spiral, named after the physicist Eugene Parker. As the sun rotates, the magnetic field lines are dragged outward by the solar wind, creating a spiral shape like water from a rotating sprinkler. This structure influences the propagation of cosmic rays and affects the magnetic environment throughout the solar system. It is a large-scale pattern, elegant and orderly, a testament to the interplay of rotation, magnetism, and flow. Eugene Parker, who predicted the existence of the solar wind in the 1950s, also made fundamental contributions to our understanding of magnetic reconnection and coronal heating. His work was initially met with skepticism, as the idea of a continuous outflow of particles from the sun seemed counterintuitive. But observations from spacecraft confirmed his predictions, and the solar wind is now recognized as a fundamental feature of the sun's behavior. Parker's insights into magnetism and plasma physics have shaped our understanding of the sun and the space around it, a quiet legacy of scientific curiosity and rigor. The magnetic field of the sun also drives the solar cycle, the periodic variation in solar activity. The cycle is thought to result from a dynamo process in the sun's interior, where the rotation and convection of plasma generate and amplify magnetic fields. Over the course of about 11 years, the magnetic field builds up, becomes tangled and unstable, and then reverses polarity. The cycle then begins again, with the magnetic poles flipped. It is a self-sustaining process, a rhythm that has persisted for billions of years, and it will continue long into the future. Magnetic fields also play a role in the life cycles of other stars. In young, rapidly rotating stars, the magnetic field can be very strong, generating powerful stellar winds and intense flares. As stars age and slow down, their magnetic activity typically decreases, though some stars remain magnetically active throughout their lives. The magnetic field affects the star's structure, its rotation, and its interaction with any surrounding planets or disks. It is a key factor in stellar evolution, influencing the star's behavior from birth to death. In binary star systems, where two stars orbit each other, magnetic fields can interact in complex ways. If one star is a white dwarf or a neutron star, and the other is a normal star, matter can flow from the normal star onto the compact object, forming an accretion disk. Magnetic fields channel this inflowing matter, creating hot spots and jets. In some cases, the magnetic field of the compact star is so strong that it disrupts the accretion disk, leading to dramatic variability in the system's brightness. These interactions are laboratories for studying magnetism under extreme conditions, where the forces are far stronger than anything we can create on Earth. Magnetism also appears in the phenomenon of stellar flares, sudden releases of energy from a star's surface. Flares are powered by magnetic reconnection, the same process that drives solar flares and auroras on Earth. In some stars, especially young, active ones, flares can be thousands of times more powerful than the largest solar flares, releasing enormous amounts of energy in a matter of minutes. These super flares can affect any planets orbiting the star, potentially stripping atmospheres or altering surface chemistry. They are reminders that magnetism, while often gentle, can also be a source of sudden, intense energy. The study of stellar magnetism has been revolutionized by space telescopes and ground-based observatories that can measure magnetic fields on distant stars. Techniques like Salmon spectroscopy detect the splitting of spectral lines caused by magnetic fields, allowing astronomers to map the field's strength and structure on the star's surface. These observations reveal that stars have magnetic fields with a wide range of strengths and geometries, from simple dipoles to complex, tangled patterns. Each star is unique, its magnetic field shaped by its mass, rotation, and evolutionary history. In the quiet moments of the night, when you look up at the stars, you're seeing not just points of light, but entire magnetic worlds, each with its own invisible architecture. The light that reaches your eyes has traveled across space, carrying information about the star's temperature, composition, and motion. But hidden in that light are also clues about the star's magnetic field, encoded in subtle shifts and splittings of spectral lines. It is a hidden layer of reality, perceptible only to those who know how to look, a reminder that the universe is far richer and more complex than it first appears. Magnetic fields also shape the structure of galaxies, guiding the flow of gas and influencing the formation of stars. In spiral galaxies like the Milky Way, the magnetic field follows the spiral arms, aligned with the density waves that sweep through the disk. This alignment helps compress the gas, triggering star formation in the arms and creating the bright, star-studded patterns we see. The magnetic field is not the primary driver of spiral structure, but it plays a supporting role, adding stability and influencing the dynamics of the interstellar medium. In elliptical galaxies, which lack the organized rotation of spirals, the magnetic field is more disordered, reflecting the random motions of stars and gas. These fields are weaker and less well understood, but they still exist, threaded through the hot gas that fills the galaxy. Observations from radio telescopes and X-ray satellites are gradually revealing the magnetic properties of elliptical galaxies, showing that even in these seemingly quiet systems, magnetism is present and active. Galaxy clusters, the largest gravitationally bound structures in the universe, also contain magnetic fields. The space between galaxies in a cluster is filled with hot, diffuse gas, and this gas is permeated by weak magnetic fields. These fields are detected through their effect on radio waves from distant galaxies, which pass through the cluster and have their polarization rotated. The origin of these cluster-scale magnetic fields is still uncertain, but they may have been amplified over billions of years by the motions of the gas and the merging of galaxies. It is magnetism on the grandest scale, spanning millions of light years. The cosmic web, the large-scale structure of the universe, may also be threaded with magnetic fields. Simulations suggest that as galaxies and clusters formed, they drew out filaments of gas connecting them, and these filaments could harbor weak magnetic fields. Detecting these fields is extremely challenging, as they are far fainter than those in galaxies or clusters, but future radio telescopes may be able to map them. If confirmed, these fields would represent the largest magnetic structures in the universe, a web of magnetism connecting the cosmic web of matter. Magnetic fields also play a role in the mysterious phenomenon of fast radio bursts, brief flashes of radio waves from distant galaxies. The exact cause of these bursts is still unknown, but the radio waves are often highly polarized, indicating that they have passed through regions of strong magnetic field. By studying the polarization and the way the radio waves are dispersed, astronomers can learn about the magnetic environment around the source of the burst. It is a new frontier in astronomy, using magnetism as a tool to probe the unknown. In our own lives, we are surrounded by magnetic fields, both natural and artificial. The Earth's magnetic field is always with us, a gentle presence that we rarely notice, but that shapes the world in countless ways. The magnets in our homes, from refrigerator magnets to the motors in our appliances, are everyday reminders of this invisible force. And the magnetic fields generated by power lines, electronics, and wireless devices are part of the modern landscape, a testament to our ability to harness and control magnetism for our purposes. Yet for all our technology, the magnetic fields we create are still dwarfed by those found in nature. The magnetar's field, the sun's corona, the galactic magnetic web, these are realms of magnetism far beyond our reach, governed by processes that we are only beginning to understand. Studying these natural magnetic fields teaches us humility, reminding us that the universe is vast, complex, and full of wonders that operate on scales and timescales far beyond human experience. And yet, we are connected to these cosmic forces, shaped by the same physical laws, made of the same elements forged in stars. As you rest and let these thoughts drift through your mind, consider the quiet presence of magnetism all around you. It is in the earth beneath you, in the air above, in the stars overhead. It is ancient and patient, a force that has shaped the universe since its earliest moments and will continue to do so long after we are gone. There is something deeply calming in this realization, a sense of continuity and connection that transcends the troubles of the day. The magnetic field does not hurry or worry. It simply exists, doing its work silently, steadily, without fanfare. The magnetic fields of distant quasars reach across billions of light years, their influence stretching through the early universe when galaxies were young and stars were just beginning to forge the heavy elements we know today. These ancient magnetic structures, detected through careful observation of polarized light, tell us that magnetism arose very early in cosmic history, perhaps even in the first 100 million years after the beginning. The fields were weaker then, more chaotic, but they were there, threading through the hot gas that would one day collapse into stars and planets. When you rest tonight, you can think of those primordial fields as the ancestors of the magnetism that surrounds you now, a lineage stretching back to the dawn of structure in the universe. Magnetic fields play a quiet role in the formation of planetary systems, helping to transport angular momentum away from collapsing clouds of gas and dust. As a young star forms, material spirals inward, and without some way to shed rotational energy, the cloud would spin too fast to collapse further. Magnetic fields, coupled to the ionized gas, act as invisible brakes, allowing matter to fall inward while angular momentum is carried outward along field lines. This process, studied through computer simulations and observations of young stellar objects, is essential to the birth of stars and their accompanying planets. It is a gentle, patient mechanism operating over millions of years, and it reminds us that magnetism is not just a force of attraction or repulsion, but also a sculptor of cosmic architecture. In our own solar system, the magnetic field of Saturn interacts with its moon Enceladus in a particularly elegant way. Enceladus, a small icy world, shoots plumes of water vapor and ice particles into space from cracks in its south polar region. These plumes contain charged particles, and as they move through Saturn's magnetic field, they create a faint but detectable disturbance, a kind of magnetic wake. Scientists have used this interaction to learn about the subsurface ocean beneath Enceladus's ice, because the conductivity of that ocean influences how the moon responds to Saturn's magnetic environment. It is a delicate dance, measured from spacecraft far away, and it speaks to the interconnectedness of worlds even across the vacuum of space. The magnetic field within a single atom is a marvel of quantum mechanics, arising from the motion and spin of electrons. Each electron generates a tiny magnetic moment, and in most materials, these moments cancel each other out, leaving no net magnetism. But in certain elements like iron, cobalt, and nickel, the electron spins a line in the same direction within small regions called domains, creating a collective magnetic field. When you hold a magnet, you are holding billions upon billions of these aligned domains, all working together in quiet harmony. The fact that such microscopic quantum properties can manifest as a force you can feel with your hand is one of the most beautiful bridges between the atomic world and our everyday experience. Magnetism also appears in the behavior of superfluids, particularly in liquid helium, 3 at temperatures just above absolute zero. In this exotic state, the helium atoms pair up and their spins align, creating a form of magnetism that is both subtle and profound. Researchers study these systems not only for their intrinsic interest, but also because they offer insights into other quantum phenomena, including superconductivity and the behavior of neutron stars. The magnetic properties of superfluid helium 3 are governed by the same fundamental principles that shape the cosmos, a reminder that the universe operates on a set of deep, interconnected rules that apply from the smallest scales to the largest. The Earth's magnetic field has a shape that extends far beyond the planet itself, forming a structure called the magnetosphere. This region, carved out of the solar wind by the pressure of Earth's magnetic field, is not a perfect sphere, but rather a teardrop shape, compressed on the side facing the sun and stretched into a long tail on the night side. Within this magnetosphere, charged particles are trapped and guided along field lines, creating regions of intense radiation known as the Van Allen belts. These belts were among the first major discoveries of the space age, detected by instruments aboard early satellites, and they remain an area of active research. The magnetosphere is a dynamic, ever-changing environment, responding to the solar wind, to storms on the sun, and to the rotation of the Earth itself. It is a shield, a laboratory, and a testament to the power of magnetic fields to shape the space around us. Some of the most beautiful magnetic structures in nature are found in the sun's corona, the outermost layer of the solar atmosphere. The corona is much hotter than the sun's surface, a fact that puzzled scientists for decades, and it is now understood that magnetic fields play a key role in heating this region. The fields store energy in twisted, stressed configurations, and when they suddenly release that energy through a process called magnetic reconnection, they heat the surrounding plasma to millions of degrees. This same process drives solar flares and coronal mass ejections, but on a quieter scale, it continuously heats the corona, creating the shimmering, structured light we see during a total solar eclipse. The corona's loops and streamers are magnetic field lines made visible by the glowing plasma that follows them, a direct portrait of magnetism painted in light. Magnetic fields also influence the chemistry of the interstellar medium, the gas and dust that fills the space between stars. In regions where new stars are forming, magnetic fields can affect the rate at which molecules collide and react, subtly altering the composition of the material that will eventually become planets and perhaps life. Some chemical reactions are sensitive to magnetic fields because they involve unpaired electrons, whose spins can be influenced by external fields. This area of study, called spin chemistry, is still being explored, but it suggests that magnetism may have played a role in the chemical evolution of the universe, guiding the formation of complex molecules in ways we are only beginning to understand. On Earth, certain plants have been found to respond to magnetic fields, though the mechanisms are not yet fully understood. Studies have shown that the growth of roots and shoots can be influenced by the direction and strength of magnetic fields, and some researchers believe that magnetoreception in plants may involve the same cryptochrome proteins found in migratory birds. If true, this would mean that plants, like animals, have a way of sensing the Earth's magnetic field and using that information to orient their growth. The idea is still speculative, but it opens up fascinating questions about how widespread magnetoreception might be in the living world, and whether it is an ancient sense that arose early in the history of life. The magnetic field of a black hole is a subject of intense theoretical interest, even though black holes themselves have no magnetic field in the classical sense. Instead, the magnetic fields we observe around black holes belong to the accretion disks and jets of material spiraling into them. These fields can become extraordinarily strong, channeling energy and matter into narrow beams that shoot out at nearly the speed of light. The study of black hole magnetism involves some of the most advanced physics we know, combining general relativity, plasma physics, and magnetohydrodynamics. It is a field where the equations are fierce and the conditions extreme, yet the underlying principles are the same ones that govern a simple bar magnet on your desk. Magnetic fields are also present in the human body, generated by the electrical activity of the heart and brain. The magnetic field of the heart is the strongest, about 1,000,000 times weaker than the Earth's magnetic field, but still measurable with sensitive instruments called magnetocardiograms. The brain's magnetic field is even weaker, yet it can be mapped using magnetoencephalography, a technique that allows researchers to study brain activity with excellent temporal resolution. These fields are not strong enough to influence our thoughts or health in any direct way, but they are a byproduct of the electrical currents that make our bodies function, a quiet reminder that we are, in a sense, electromagnetic beings. The process by which magnetic fields are generated in planets, stars, and galaxies is called the dynamo effect, and it relies on the motion of conducting fluids. In the Earth, this fluid is molten iron in the outer core. In the Sun, it is ionized hydrogen and helium. In galaxies, it is ionized gas moving through space. The dynamo effect is a self-sustaining process. Motion generates a magnetic field, and the magnetic field influences the motion, creating a feedback loop that can persist for billions of years. The mathematics of dynamo theory is complex involving nonlinear equations that are difficult to solve, but the basic idea is simple and elegant. It is a process driven by motion and sustained by the interplay of forces, a cosmic engine that runs quietly in the background of the universe. Magnetic reconnection, the process by which magnetic field lines break and rejoin, releasing energy, is one of the most important phenomena in space physics. It occurs in the Earth's magnetosphere, in the Sun's corona, and in distant astrophysical environments. During reconnection, magnetic energy is converted into kinetic energy, heating particles and accelerating them to high speeds. This process is responsible for the sudden release of energy in solar flares, for the auroras that light up our polar skies, and for the dynamics of plasma throughout the universe. Reconnection happens quickly, on timescales of seconds to minutes, but its effects can be felt across vast distances. It is a reminder that magnetic fields, though invisible, are dynamic and powerful, capable of reshaping the space around them in dramatic ways. The magnetic fields of distant stars can be measured through a technique called Zeeman splitting, which detects the way magnetic fields split spectral lines of light. When atoms emit light in the presence of a magnetic field, the energy levels of their electrons are slightly shifted, causing the emitted light to split into multiple components. By measuring this splitting, astronomers can determine the strength and structure of stellar magnetic fields, even for stars hundreds or thousands of light years away. This technique has revealed that many stars have magnetic fields far stronger than the Sun's, and that these fields play a crucial role in stellar activity, influencing everything from star spots to stellar winds. Magnetic fields are also crucial in the formation of structure in the universe. On the largest scales, magnetic fields thread through galaxy clusters and the filaments of the cosmic web, influencing the flow of gas and the formation of galaxies. These fields are incredibly weak, millions of times weaker than the Earth's field, but they extend across millions of light years, making their total energy significant. The origin of these large-scale fields is still debated, with some scientists proposing that they were generated in the early universe, while others suggest they were amplified over time by the motions of galaxies and gas. Either way, they are a fundamental part of the cosmic landscape, shaping the universe in ways both subtle and profound. The study of paleomagnetism, the record of Earth's ancient magnetic field preserved in rocks, has revolutionized our understanding of geology and the history of our planet. By measuring the direction and intensity of magnetization in ancient rocks, scientists can reconstruct the positions of continents, the timing of mountain-building events, and the history of the Earth's magnetic field itself. This field has provided some of the strongest evidence for plate tectonics, showing that continents have moved over time and that the ocean floor is constantly being created and destroyed. It has also revealed that the Earth's magnetic field has reversed hundreds of times, with North and South poles swapping places in events that are recorded in the rocks like pages in a book. Magnetic fields in the ocean are generated by the movement of seawater, which contains dissolved salts and is therefore electrically conductive. As ocean currents flow through the Earth's magnetic field, they generate weak electric currents, which in turn produce their own magnetic fields. These fields are extremely faint, but they can be measured with sensitive instruments deployed on the seafloor or towed behind ships. Studying these oceanic magnetic fields helps scientists understand ocean circulation, the transport of heat and nutrients, and the interaction between the ocean and the Earth's magnetic field. It is yet another way that magnetism weaves through the natural world, connecting processes that might seem unrelated. The magnetic field of a neutron star, as we discussed earlier, can be unimaginably strong, but there are also objects called low-field magnetars, which have magnetic fields that, while still intense by any normal standard, are weaker than those of typical magnetars. These objects challenge our understanding of how magnetic fields are generated and sustained in neutron stars, and they suggest that there may be a continuum of magnetic field strengths rather than distinct categories. Studying these objects helps astronomers refine their models of stellar evolution and the physics of extreme matter. And it reminds us that the universe is full of surprises, with objects that defy easy classification. Magnetic fields also play a role in the behavior of cosmic dust, the tiny particles that float through space and are the building blocks of planets. Dust grains can become aligned with magnetic fields, and this alignment affects the way they scatter and polarize light. By measuring the polarization of light from distant stars and galaxies, astronomers can map the magnetic fields in the regions where the light has passed through dust. This technique has been used to study the magnetic fields in our own galaxy, in nearby galaxies, and even in the regions around forming stars. It is a powerful tool, turning the humble dust grain into a probe of invisible magnetic structures. The interaction between magnetic fields and the solar wind creates a variety of phenomena throughout the solar system, from the auroras on Earth to the magnetic tails of comets. Comets, as they approach the sun, develop a tail of ionized gas that is shaped by the solar wind and the sun's magnetic field. This tail always points away from the sun, stretched out by the pressure of the solar wind, and it can extend for millions of kilometers. The magnetic field embedded in the solar wind drapes around the comet, creating a complex, dynamic structure that changes as the comet moves through space. Observing these interactions helps scientists understand the properties of the solar wind and the way magnetic fields behave in the tenuous plasma of interplanetary space. Magnetic fields are also present in the atmospheres of certain exoplanets, the planets that orbit stars other than the Sun. Detecting these fields is extremely challenging, but astronomers have developed techniques based on the interaction between the planet's magnetic field and the stellar wind from its host star. When a planet with a strong magnetic field orbits close to its star, the interaction can produce radio emissions, similar to the auroras on Earth, but much more intense. By detecting these emissions, astronomers hope to learn about the magnetic fields of exoplanets, which in turn tells us about their interiors, their atmospheres, and their potential habitability. It is a frontier of research, pushing the limits of our instruments and our understanding. The magnetic field of the Milky Way, our home galaxy, has been mapped in increasing detail over the past few decades. The field follows the spiral arms of the galaxy, threading through the gas and dust that fills the space between stars. It is generated by a galactic dynamo, driven by the rotation of the galaxy and the turbulent motions of gas. The field strength varies from place to place, but on average it is about 1,000,000 times weaker than the Earth's field. Despite its weakness, the galactic magnetic field plays an important role in the life of the galaxy, influencing the formation of stars, the propagation of cosmic rays, and the structure of the interstellar medium. It is a vast, invisible architecture that holds the galaxy together in ways we are still learning to appreciate. Magnetic fields can also affect the way we perceive the night sky. The polarization of starlight, caused by dust grains aligned with magnetic fields, can be measured with specialized instruments, revealing the hidden structure of the magnetic field in our galaxy. This polarization is subtle, typically only a few percent, but it carries valuable information about the direction and strength of the field. By mapping the polarization of light from thousands of stars, astronomers have created detailed maps of the galactic magnetic field, showing how it winds through the spiral arms and loops above and below the galactic plane. It is a hidden layer of the cosmos, invisible to the naked eye, but revealed through careful observation and analysis. The study of magnetic fields in nature is a study of connection, of the invisible threads that link the smallest particles to the largest structures in the universe. From the spin of an electron to the rotation of a galaxy, magnetism is a fundamental force that shapes the world around us. It is a force that guides birds across continents, that protects our planet from the solar wind, that powers the most energetic explosions in the universe. And yet, for all its power, It is a gentle force, one that operates quietly, patiently, over timescales that stretch from fractions of a second to billions of years. As you lie here, breathing slowly, you are surrounded by magnetic fields. The Earth's field wraps around you, a protective cocoon that has been there since long before you were born and will remain long after. The faint magnetic fields of your own body hum with the rhythm of your heart and the activity of your brain. And beyond, in the vast expanse of space, magnetic fields stretch across distances that dwarf the human imagination, connecting stars and galaxies in a web of invisible influence. These fields are not separate from you. They are part of the same universe, governed by the same laws, woven from the same fundamental forces. Magnetic fields remind us that the universe is more than what we can see. So much of reality is hidden from our direct perception, detectable only through instruments and careful observation. Yet these hidden aspects are just as real, just as important as the things we can touch and see. The magnetic field that guides a bird is as real as the bird itself. The field that shapes a galaxy is as real as the stars within it. And the field that surrounds the Earth is as real as the ground beneath your feet. Learning to appreciate these invisible aspects of nature is a way of deepening our connection to the world, of seeing beyond the surface to the deeper patterns that govern existence. There is something deeply calming about the constancy of magnetic fields. They change, yes, but they change slowly, on timescales that are often far longer than a human lifetime. The Earth's field has been reversing for hundreds of millions of years, but each reversal takes thousands of years to complete. The magnetic field of the Sun goes through an 11-year cycle, but the cycle is regular, predictable, a cosmic clock that has been ticking for billions of years. Even the magnetic fields of distant galaxies, though shaped by violent processes, evolve over millions and billions of years. In a universe that can seem chaotic and unpredictable, magnetic fields offer a kind of stability, a reminder that there are patterns and rhythms that endure. The beauty of magnetic fields lies not only in their effects, but in their simplicity. The fundamental equations that describe magnetism, Maxwell's equations, are elegant and concise, a set of 4 mathematical statements that capture the essence of electric and magnetic phenomena. These equations, formulated in the 19th century, have stood the test of time, remaining unchanged even as our understanding of the universe has deepened. They describe everything from the behavior of a simple magnet to the propagation of light, from the auroras to the jets of black holes. It is a testament to the unity of nature, to the fact that a few simple principles can explain an astonishing variety of phenomena. Magnetic fields also inspire a sense of wonder, a recognition that the universe is full of mysteries waiting to be explored. Despite centuries of study, there is still much we don't understand about magnetism. We don't fully understand how the Earth's magnetic field is generated or why it reverses. We don't know the origin of the large-scale magnetic fields that thread through the cosmos. We don't understand all the ways that living organisms sense and respond to magnetic fields. Each of these questions is an invitation to explore, to observe, to think deeply about the nature of reality. And each answer we find opens up new questions, new mysteries, new opportunities for wonder. As you rest here, let yourself be held by the knowledge that you are part of a vast, interconnected system, a universe shaped by forces both visible and invisible. The magnetic fields that surround you are ancient, arising from processes that began billions of years ago and will continue long into the future. They connect you to the Earth, to the Sun, to the stars, to the very fabric of space and time. You are not separate from these forces. You are woven into them, a small but integral part of the cosmic tapestry. The story of magnetic fields is a story of patience and persistence. It is a story of forces that act quietly, over long periods, shaping the universe one small interaction at a time. It is a story of discovery, of scientists peering into the invisible, using instruments and mathematics to reveal what cannot be seen. It is a story of connection, of the way that everything in the universe is linked, from the smallest particle to the largest galaxy. And it is a story of beauty, of the elegance and simplicity that underlies the complexity of the natural world. Magnetism teaches us that strength does not always announce itself loudly. The most powerful forces in the universe often work silently, invisibly, their effects felt only indirectly. The magnetic field that protects the Earth does not blaze across the sky. It works quietly, deflecting particles, shaping the space around us. The magnetic field that guides a migrating bird does not shout. It whispers, a subtle signal that the bird has learned to interpret. The magnetic field that threads through a galaxy does not demand attention. It simply is a presence that shapes the flow of matter and energy over billions of years. There's a lesson in this, a reminder that the most important things in life are often the quietest. The love of a friend, the steady rhythm of breath, the slow turning of the seasons. These are the things that sustain us, that give life meaning and depth. Like magnetic fields, they work in the background, shaping our experience in ways we may not always notice, but that are nonetheless essential. To appreciate these quiet forces, we must slow down, pay attention, cultivate a sense of wonder and gratitude for the subtle patterns that surround us. As you lie here, breathing slowly, let yourself sink into the quiet. Let go of the noise and the rush, the worries and the plans. There is nothing you need to do right now, nowhere you need to be. You are here, in this moment, held by the Earth, surrounded by invisible fields that have been here for eons and will remain long after. You are safe, you are supported. You are part of something vast and ancient and beautiful. The magnetic fields of nature are a gift, a reminder that the universe is full of wonders both seen and unseen. They are a bridge between the human and the cosmic, between the everyday and the extraordinary. They are a source of knowledge, of inspiration, of comfort, and they are always there, quietly shaping the world, connecting all things in a web of invisible influence. Let yourself rest in that knowledge. Let it soothe you, calm you, carry you gently towards sleep. The magnetic fields will still be there when you wake, as they have always been, as they will always be. They are a constant, a presence, a quiet assurance that the universe is ordered, beautiful, and full of mysteries waiting to be discovered. And so, as we come to the end of this journey through the magnetic fields of nature, let yourself feel the peace that comes from understanding, the calm that comes from connection. You have traveled from the core of the Earth to the edge of the observable universe, from the smallest atom to the largest galaxy. You have seen how magnetism shapes the world, how it guides and protects, how it connects all things in a vast, invisible network. And now, as you rest, you can carry that knowledge with you, a gentle light in the darkness, a reminder that you are part of something greater. The universe is vast, but you're not lost in it. You are held, supported, connected. The magnetic fields that surround you are a symbol of that connection, a reminder that you belong here, that you are woven into the fabric of existence. And as you drift towards sleep, you can rest easy in that knowledge, knowing that you are safe, that you are part of the great, unfolding story of the cosmos. Sleep well, dear traveler. Let the magnetic fields cradle you. Let the quiet hum of the universe lull you into rest. There are more stories to tell, more wonders to explore, but for now, simply rest. The universe will be here when you wake, as beautiful and mysterious as ever, waiting to share its secrets with you once more. Good night.